Okay, so here we have class 18, where we're going to do an acceleration analysis using the vector loop method for a 4-bar and a crank slider. So this is the lecture portion, and I will separate out and do different videos for the 4-bar and crank slider examples. So the acceleration of a typical vector in complex notation. We took the velocity and we took the derivative of it, and for that position we were able to find the velocity. All right, so that's just of a simple scenario, right, where we have a linkage which is represented by a position vector, right, where we have theta right here, and we have a magnitude of p, right, and then and we represent that position vector by p times e to the j theta. So when we take a derivative of it, and as long as p doesn't change, we have pj e to the j theta times d theta dt, and that's where the omega comes from. Now, if we to get the acceleration, we could just take a derivative of this velocity vector. So taking the derivative, so we get we get a jp to the outside of this thing, right? So I took this j and this p and I moved these outside, and then we take the derivative. And we see that we have to take the first, it's a product rule, so we take the derivative of omega with respect to time, which is going to be alpha, and then we have to do the other part of it, so we take the omega and we get a j that also drops out from it after we took the time derivative of ej theta again, and we notice that d theta dt that drops out is also an omega. We also note that we're going to multiply that jp back by it again, and having that j squared turns into a negative sign. And so you might recognize that what we have right here is alpha times r and then omega squared times r. So these are the normal and the tangential components. Interesting how that turns out, and that negative comes out, which we should be familiar with from our review of acceleration in dynamics. So this is the statement that we can make for just a generic typical vector in complex notation. And we note how it looks like the relative acceleration here is broken down into tangential and normal components, where the tangential is just p alpha j e to the j theta, and the normal is negative p omega squared e j to the theta. Sometimes in the book they sometimes use capital A and they use superscripts, just so you know. If we go ahead and we substitute back in the Euler identity, okay, then we go back and we substitute in the Euler identity, and we would get this phrase right here. So we could do that later. For that, now that is the situation where we have just a generic vector, and we have so we're showing it right here. For whatever reason, they decided to make the velocity negative right here, but it doesn't matter if the velocity is negative. The normal component is pointing downwards towards the center, and that's really what that negative means, by the way, is that it's pointing towards the center. You also notice that they're perpendicular to each other, which is represented by the fact that this has a j in it and this one doesn't, right? That's what makes them perpendicular. And this right here is just showing that they've just taken the Euler identity and pre-multiplied j by it. That's why that's a negative sign of theta times the thing. So now this is for if we just had a linkage, but now if we have a linkage that's moving, right? So this other one over here, this is very similar to just having a crank or having a rocker. But if we have the coupler, that's actually moving, right? So we take a reference, and most often it's going to be the joint, between the crank and the coupler. And we use that, and we have the acceleration, and they're just showing it in the pure x direction here. But that becomes the reference. And so it's really just the same stuff, but just with a moving reference. And I should say a translating reference, because we could actually have some issues if it was a rotating reference. But no, we're okay then. Never mind. I'll take that back. So for a 4-bar mechanism, we have this condition right here where we could take a look and see the various acceleration components of each, right? And so make sure that we take a look at, here are the rigid ones, or not the rigid ones, but the pinned accelerations. And then we also have a moving one. So here's the one that we're going to care about for the coupler. Remember that so that's a visualization really of what's taking place in the 4-bar. We could just methodically go through our procession when using a vector loop and define the vector loop. Once again, remember, it's a loop traveling around each of the position vectors in that direction. And we could write out those position vectors just as we had before. And if we took the velocity, remember that we found it to equal here, especially because d went away, because d doesn't change. And now if we take the time derivative of this and group it, all right, so we have the time rate change of that velocity, we have the time rate change of this velocity, and then the time rate change of this velocity. And all of them have different parts. So you can see that this right here is the acceleration of A. That's going to be right up here. And the acceleration of B with respect to A, it's right here, and shows up right here. And then the acceleration of B itself right here. So this is the acceleration of point B that's represented by here. And the unknowns that are inside this when we go through a typical problem are going to be the angular accelerations. So we have a function of that angular acceleration of 3, right? So it's typically going to be the coupler's angular acceleration is a function of the lengths of all the pieces, the positions at that time, and the angular velocities at that time, and then the angular acceleration of the input, the crank. And very similar for the other angular acceleration, the angular acceleration of the rocker. If we go to put in the unknowns, right, to find these unknowns, we substitute in Euler's identity, and what we're left with when we come through this is this equation. Now we could stretch all this out, rearrange it, and group it, and we're left with these two equations, where the only two unknowns are alpha 3 and alpha 4. And so the rest of them are knowns, or things that we found during the position analysis and the velocity analysis. So we had to do those first to get to this point, and then we can find what the alphas are. And so the solution that Shigley has, not Shigley, but excuse me, I think I'm missing something here, so let me make sure that I fill that out before I go any further here. So let me also, I wanted also to meant to name what these equations are going to be, right? So when we flip to right here, so try to make some noise here. The 4-bar slider crank. Nope, I wanted to go to the linkage analysis. Okay. Where are you? Where are you? Okay, here's the... Okay, yes. So these are equations 7, 12, A and B. So all of these are equations 7, 12 right here. And this should be CE minus BF. And then there should be A divided by AE minus BD. So I'm not sure why those aren't in my notes, but I'll make sure that I put them in. And all of these we just substitute in these values right here, where you can see that C and F are rather long things, but they just did the algebra for you. I guess that was kind of nice of them, right? Kind of a long thing, but it sort of ends with the trend of Norton's method. And once these once alpha 3 is found and alpha 4 is found, then we could go back and we could find what the accelerations of at the different points are going to be. Where that's the acceleration at A. Now, actually, we could have found the acceleration of A and the X and the Y direction right from the very beginning, because usually that's an input. So you'll see we didn't need those. And we could find the acceleration of B from this right here. So it's up here is the acceleration of B, and we could find these two parts right here. And notably that these are actually written in the book, by the way. This is, I just gave them a different symbol here in the front, but these are equations 7.13. And then we have the relative acceleration of B with respect to A, right? So this is the one represented by the coupler. Quite often we want to get on a coupler curve. So instead of writing out the B with respect to A, we could make this a P with respect to A, and really the only things that are going to change, we would replace B's with AP and replace theta 3 with theta 3 plus whatever the coupler curve is, remember, or whatever the coupler angle is. So like we'll make it look like this right here. All right, so that right there is going to be our del. Right here is our theta 3 onto the thing, and then right here is our AP distance. So now we're able to find what the acceleration is going to be at point P with this information up above, and it doesn't change all that much. From another book, this is how do you pronounce this guy's name? Myszka's. In Myszka's book, he gives a closed form solution. So I walk through, and it's in his chapter on acceleration. So right here we see what we've done here is we went to position analysis right here. Here's velocity analysis right here. And then we could do an acceleration analysis. So he does a closed form, and you should get the same thing. You got to be careful, of course, when you're doing the position analysis that you don't end up with the crossed configuration. So if you just simply plug and chug into this, you have the potential to do that. All right. I'll do the example in another video, and let me walk through the crank slider and slider crank. They're the same, really, analysis. They just have different solutions when you get to the end. So we have this condition right here where we're now the vector loop comes. We are going this right here, but one of the differences is that they've made this vector, they changed the direction of that vector. So we actually have the sign changes right here, because as we go through the loop, we're going backwards away from the vector arrow in the position vector, that is. And we wrote out the vector loop basic equation using the polar notation, the complex notation this way. And when we took the time derivative, we got this velocity scenario right here, noticing that C went away because this was a fixed distance for the offset. And we might actually want to call this an offset crank slider or an offset slider crank. But anyway. If we take the time derivative of that velocity again, we get this first part, That's going to be the acceleration here at the crank. We'll get the acceleration of the conrod relative to the crank, and then we get the acceleration of the piston. And if we rearrange these to represent this the relative acceleration main go-to equation that ties all these things together, this is how I'm trying to explain and tie it back to dynamics. We'll see that these are the representations of those accelerations. And also note that inside them, we have the tangential and the normal components. And I decided for some reason to call this tangential. I don't know if that makes a whole lot of sense, but I stuck that in there. It is kind of a quasi-tangential type of thing, I guess. I don't know. It's a stretch. Now, if you want to, once we get done and substituting the Euler identities, which I didn't do here, but I think it is done in the book so that you can look it up and you could see for yourself. You can, when you go for the crank slider, where in the crank slider it's the alpha 3 and the D double dot, right? So it's the acceleration of the piston and the angular acceleration of the conrod that are unknown. So we could find that angular acceleration of the conrod from this, and we could find the acceleration of the piston, the linear acceleration of the piston from here, where you need to know this first, by the way, because it's buried within inside here. For a slider crank problem, the two unknowns are the angular accelerations, because of course we have an input which is going to be D, and so right here this D double dot is actually an input, and for some reason there's like missing something right here. So let me double check and see what that is. It might be that I got rid of it because I thought I was making a mistake. So let me double check. The slider crank, they show theta 2, and I mean alpha 2. Alpha 2, it should be in the denominator the cosine of theta 3. I don't know why that's randomly not there. All right, and then we come to this next one, and we get the alpha 3, and sure enough. And we say, do we need, yeah, we do need alpha 2 to be able to find alpha 3, just so you know. So we had to find that alpha 2 before finding the alpha 3. And these are equations 717, by the way, in the book, and they're on page 364 if you happen to be using the 5th edition. So and then lastly, here's Myszka's equations that they provide, and you got to be careful if you're using these because they use a different theta 3 as the reference. So just be careful of plugging and chugging. You come through here and you start using these equations because they look simpler and they're quicker. You're going to get mixed up because this one has theta 3 as being between the horizontal and this side of the vector, whereas this guy uses theta 3 from here and goes all the way back over there, right? So it's not the interior one. It's also, I don't know, I'm going to say this the right way, is this, yeah, this is, they actually by default make like the offset, like they make the piston below the hinge joint. So those are differences to be on the lookout for. So that's the main lecture portion of this. I wonder if anybody actually listens to these. So we'll discard all of this, and I don't think I'm going to add anything to the end of it. It's already 20 minutes long. Right here, we are printing something, so apologize for all that noise in the background. We're printing masks, shields for hospitals, and let's see Nope, this one got screwed up again too. So, damn, I got to throw another one away. Have a good day.